Good morning everyone. Myself R. Venkatesh, working as Assistant Professor in the Department of Computer Science and Engineering at Vignan Smirula. Today I am going to discuss about one of the important topic in cryptography and network security, that is data encryption standard, DES. So DES is a symmetric block cipher. So symmetric is nothing but for both encryption and decryption purpose we are using the same key. Okay, so there is nothing but the same key will be used for converting the plain text to ciphertext and ciphertext to plain text. So before going to data encryption standard, we have to know the fundamental concepts of DES. Okay, so coming to the first one, both encryption and decryption keys are the same and are kept secret. Okay, so in order to transfer the data between the sender and receiver, so first the sender needs to encrypt the message, then it has to forward to the receiver, and at the receiver end, so the receiver convert the ciphertext to plain text by using the same key. Okay, so here both encryption and decryption keys are the same and are kept secret. Okay, so these two keys will be, that means the same key will be used between the two parties, and the key will be kept secret. So the secret key must be known at both ends to perform encryption and decryption. So in order to convert the plain text to ciphertext and ciphertext to plain text, the key must be known between the two participants. Okay, so the secret key algorithms are fast and they are used for encrypting or decrypting high volume of data. Okay, so the key will be secret between the two participants, so it is called as secret key cryptography. So there are two types in secret key cryptography. The first one is block ciphers and the second one is stream ciphers. Coming to the first one, stream ciphers. So a stream cipher is a type of symmetric encryption in which input data is encrypted one bit at a time. Okay, so the stream cipher is a symmetric encryption. That means we are using the same key for both encryption process and decryption process. So to convert the plain text into ciphertext and ciphertext to plain text, we are using the same key. So it is called as a symmetric encryption. Okay, now the input data is encrypted one bit at a time. So in the stream ciphers, the data will be encrypted one bit at a time. Okay, so the examples of stream ciphers include seal, 2', RC4 and EFI. The second one is block cipher. A block cipher is a type of symmetric encryption which operates on a block of data. So the block cipher is entirely different to stream cipher. So in the stream cipher, we can convert the plain text to ciphertext by bit at a time, whereas in the block cipher, we can convert the block of data from plain text to ciphertext. Okay, so the modern block ciphers typically use a block length of 128 bits or more. So examples of block ciphers include DES, AES, RC5 and IDF. Okay, so here in the block cipher, we can convert a block of data into ciphertext. Okay, so you can see the diagram here. So I'm having a plain text of length 64 bits and I'm having an encryption algorithm and I'm having a key. So by using the encryption algorithm and key, so I can convert the plain text of 64 bits to ciphertext of 64 bits. Okay, so the length of a plain text block is 64 bits and the size of the ciphertext block is also 64 bits. So a block cipher breaks the message into fixed size block. Okay, so it can convert the message into number of blocks and which can take one block at a time and transform it into another block of the same length using a user provide secret key. Okay, so the block cipher which take a block of data as a plain text and which can convert the plain text into a block of ciphertext, that means the same length using a user specified key. Okay, so the key will be secret between the sender and the receiver. And the decryption is performed by applying the reverse transformation to the cipher text block using the same secret key. Decryption is nothing but performing a reverse operation of a encryption process. Okay, So the key will be same for both encryption purpose and decryption purpose. So most symmetric block ciphers are based on a physical cipher structure. So the next one is the properties of good ciphers. Okay, so here you have to know the two fundamental things. The first one is confusion and diffusion. So the confusion and diffusions are two properties of the operation of a secure cipher which are identified by Shannon. So confusion refers making the relationship between the key and the cipher text as a complex and involved as possible. That means confusion which hides the relationship between the key and the cipher text. So whereas the diffusion refers the property that the redundancy in the statistics of the plain text is dissipated. So in the statistics of the cipher text. That means so which hides the relationship between the plain text and the cipher text. So confusion which hides the relationship between the key and the cipher text, whereas the diffusion which hides the relationship between the plain text and the cipher text. So coming to the next one, a motivation for the physical cipher structure. So here we are having a SP network. So that means substitution and permutation. So the product cipher is nothing but the combination of substitution and permutation ciphers. Okay, so whereas the substitution technique is nothing but we are replacing the bits either with 0 or 1 and in the transposition technique we cannot replacing the bits, we are just rearranging the bits or we are reordering the bits. So the combination of both these techniques are called product cipher. So two or more simple ciphers are performed in sequence in such a way that the final result or product is cryptographically stronger than any of the component cipher. Okay, so you can see the structure of a physical cipher here. So the physical cipher structure contains three parts. So the first one is we have to partition the input block into two halves, left half and right half. Then process through multiple rounds which perform a substitution on the left data half based on the round function of right half and subkey. The final one is you have a permutation swapping halves. You can see the diagram here. So I'm having a plain text and the plain text will be divided into two halves, left half and right half. So the right half will be input as a function along with the key, and the output of that function will be XORed with the left half. Again the left half and the right half will be swapped together, and again the right half will be input as the left half for second round, and the left half will be input as a right half for the second round. So this process will be continued to multiple rounds. So coming to the introduction of data encryption standard. So the DES is a symmetric key block cipher published by National Institute of Standards and Technology. So DES is a symmetric key block cipher. That means symmetric is nothing but for both encryption process and decryption process we are using the same key. Okay, so on the block cipher is nothing but so which can process the data in the form of blocks. In 1973, NIST published a request for a proposal for a national symmetric key encrypto system. So a proposal from IBM, a modification of the project called Lucifer, and was accepted as a DES. So DES is a block cipher and encrypts the data in blocks of size of 64 bit each. So the size of blocks is 64 in DES. So that means 64 bits of plain text goes through input to the DES function which produces 64 bits of ciphertext. So which takes 64 bits of input and which can convert those 64 bits input into 64 bits of ciphertext. So the same algorithm and the key are used for encryption and decryption process with the minor differences, and the key length is 56 bits. Okay, so for the encryption process and for the decryption process, we are using the same length key and the same algorithm. So to convert the plain text into ciphertext and ciphertext to plain text. So the DES is an implementation of a physical cipher. So it is also a symmetric algorithm. So it uses a 64-bit key, whereas 56 bits make up the true key and the 8 bits are used for parity. So actually the DES uses a 64-bit key. So 8 bits are for padding purpose and the remaining 56 bits will be the actual key. So you can see the diagram here. I'm having a encryption process and the decryption process. So in the encryption process, the DS cipher takes 64 bit of plain text, and which can convert the data into 64 bits of ciphertext. And at the decryption side also, which can take the 64 bit of ciphertext, and the DS reverse cipher, which can convert the ciphertext into 64 bit of plain text. And these two encryption and decryption process can take same length key, that is 56 bit key for converting the plain text into ciphertext and ciphertext to plain text. So this is the general structure of data encryption standard. So the 64-bit plain text will be forwarded to the DS function, where we are having the initial permutation before round 1. So after the initial permutation, the data will be forwarded to round 1. So in the DES we are having totally 16 rounds. So for each round we are providing a separate key of length of 48 bits, so which is generated by a round key generator. So after performing the 16 rounds, so the output will be forwarded to final permutation, so where we are rearranging the bits, and finally we can get a 64 bit of ciphertext. So coming to the description, so the DES operates on 64-bit blocks of plain text. So after an initial permutation, the block is broken into two halves, left half and right half, and having a same length. Okay. So the 64-bit blocks of plain text will be divided into two halves, left half and right half, and the length of the left half is 32 bits and the right half is 32 bits. So there are 16 rounds of identical operations called function f, in which data are combined with 16 keys of 48 bits, one for each round. So we're having totally 16 rounds in DES, and for each round we are providing one separate key of length 48 bits. So like that we are having 16 keys. Okay, so we are having 16 rounds totally, so we have to provide 16 keys. So after the 16th round, the right and left halves are joined, and the final permutation finishes the algorithm. So because DES operation is very repetitive, it is readily implementable in hardware as well as software. So the next one is initial and final permutation. The initial and final permutations are straight permutation boxes that are inverse of each other. So the straight permutation boxes are nothing but where we are having same number of inputs and we are getting same number of outputs. Okay, so the initial permutation happens only once, and it happens before the first round. So it suggests how the transposition in IP should process. So permutation is nothing but transposition of a bits. That means we are rearranging the bits based on predetermined process. Okay, so it happens before the first round. So bits in the plain text are moved to next location. So you can see the example in the next diagram. Okay, so that means the bit 58 to bit 1, 50 to bit 2, and bit 42 to bit 3. So this is the diagram which represents the initial and final permutation steps in DES. So you can see the diagram here. So I'm having initial permutation. After that I'm having 16 rounds, and after the 16th round I'm having the final permutation. So you can see the initial permutation where we are having the mappings between inputs and the outputs. Okay, so the first bit will be mapped with the 40th bit, and the second bit will be mapped with the 8th bit, and the 50th bit will be mapped with the first bit. Like that we are having different types of mappings between the inputs and outputs. So you can consider this table, initial permutation and final permutation. Okay, so we're having a totally of 64 bits, so 1 to 64. Okay, so I can consider the first bit of initial permutation, we're having 58. That means the first output will be generated from the 58th bit. And you can consider the second bit, which is having 50. So the second output will be from 50th bit, and the third output will be 42nd bit. The fourth output will be 34th bit, and the fifth output will be 26th bit. Like that we are having rearrangements in a initial permutation. And the reverse of the initial permutation is final permutation. Okay. So the next one is rounds. So the DES uses 16 rounds. Each round of DES is a crystal cipher. So you can see the diagram here. So I'm having the plain text of 64 bits. So that 64 bits will be divided into left half and right half. So the length of the left half is 32 bits and the length of right half is 32 bits. Now you can consider, so the two halves will be forwarded to mixer, where the right half will be the input of function and along with the key k1. Okay, so the function performing operation on the right half and the key, and which generates an output, and that output will be XORed with the left half of the plain text, and which generates an output, and that will be forwarded to the swiper. Now the swiper can swap the left half and right half, and now the right half of the plain text will becomes the left half of the next round, and the left half of the plain text becomes the right half of the second round. So this process will be continued up to 16 rounds. So the next one is DES function. So the heart of DES is the DES function. So the DES function applies a 48-bit key to the rightmost 32 bits to produce a 32-bit output. Okay, so we're having four sections in DES function: expansion D box, whitener, group of S box, and straight D box. So you can consider the diagram here. So I'm having a function. So I'm forwarding 32 bits to the expansion P box. So where the 32 bits will be expanded to 48 bits because the length of the key here is 48. Okay, so in order to XOR with the key, so first of all you have to expand the 32 bits into 48 bits by using expansion P box. Okay, so after expanded to 48 bits, now we are performing the XOR operation on the input and the key, so which generates a 48 bits of output. So that 48 bits of output will be forwarded to S boxes, so where we are having 8 S boxes, and based on the S boxes, the 48 bits output will be generated as a 32 bits of output. Now that 32 bits will be forwarded to straight P box, where we're having the mappings between the inputs and the outputs. So expansion D box. So since right input is a 32-bit and a round key is a 48-bit, so first of all you need to expand the right input to 48 bits. Okay, so during the expansion permutation, the right input is expanded from 32 bits to 48 bits because the length of the key is 48 bits, but I'm having the input as 32 bits. So in order to perform XOR operation, these two, first of all you need to expand the 32 bits into 48 bits. So by using the expansion debox, you can convert the 32 bits into 48 bits, and then you can perform an XOR operation on the same length key and the plain text. So this happens as a 32-bit input is divided into 8 blocks, so with each block consisting of 4 bits. Now the 32 bits will be divided into 8 halves, and each block consisting of 4 bits. So then 4-bit block of the previous step is then expanded to a corresponding 6-bit block. For 4-bit block, 2 more bits are added, and you can see the table here how the expansion permutation can be done. So the next one is whitener. So after the expansion permutation, the DES does XOR operation on the expanded right section and the round key. So after converting 32 bits into 48 bits, now we have to perform an XOR operation on the plain text and the key. Now both the round section and the key are 48 bits in length, so the round key is used only in this section. So after converting the 48 bits of plain text, now we have to perform an XOR operation on this key and the plain text. So next one is S boxes. So the S boxes do the real mixing. That means in DES we are having a totally of 8 S boxes, each with a 6-bit input and 4-bit output. That means so each S box takes 6-bit input and which can generate say 4-bit of output. So the substitution boxes provides a substitution code. That means there is a code output stored for each input. So each S box stores a different set of 48 hexadecimal numbers in a matrix of 16 into 4. So which contains a matrix of 16 columns and 4 rows. So there are 8 S boxes in DES. So each accepts a 6-bit input and return a 4-bit output. We can see the substitution boxes here. So we're having a totally 8 S boxes. So which maps the 6-bit input to 4 bits of output. So each S box is exactly 4 little 4-bit boxes. So the outer bits 1 and 6 select the rows, and the inner bits, that means the middle bits 2 to 5 are substituted, and the result is 32 bits. Okay, so you can see how the function will be performed. So the 32 bits will be expanded to 48 bits based on the expansion permutation. So after that, we have to perform the XOR operation on both the text and key having same length. Now, after performing the XOR operation, the output will be forwarded to S boxes. So now the S boxes are generated output and which forwarded to a permutation box. So now the permutation box is rearranging the bits and which generates say 32 bits. So you can consider an example. So S box 1. So the input to S box 1 is 1000011. So what is the output? Okay. So if we write the first and the 6th bits together, so we get 11 in binary, because you can see in the previous slide. So here the outer bits 1 and 6 select the rows, and inner bits 2 to 5 are for columns. Okay, so now in this example, so the outer bits will be 1 and 1. That means that the left bit and the rightmost bit will be 1 and 1. So those bits will be represent the rows, and 0001 which represents the column value. So now we can consider, so the 11 will be represented the row value. So 11 in binary, so which is 3 in decimal. So the remaining bits are 0001 in binary, so which is 1 in decimal. So now we have to verify row 3. So we look for the value in the row 3 and column 1. So from the table S box 1, so the result is 12 in decimal. So we can convert the 12 into binary, so we can get 1100. So the input 1000011, so which generates an output of 1100. Next one is straight permutation. So the 32-bit output of S boxes is then subjected to the straight permutation. Okay, so here you can see the 7th bit of the input becomes the 2nd bit of the output, and the 16th bit of the input becomes the 1st bit of the output. Like that, we have to perform the straight permutation. So this is DES cipher and reverse cipher for the first approach. So the plain text will be divided into 2 halves, left half and right half, and that will be forwarded to different types of rounds, and finally we can get a cipher text. So now the next concept is key generation. So the round key generator creates 16 48-bit keys out of a 56-bit cipher key. So the actual length of key is 56 bits. So now that 56 bits will be forwarded to round key generator, where the round key generator generates a new key for each round. So totally we are having 16 rounds. So for each round, the round key generator generates a new key. So the cipher key is normally given as 64-bit key, in which 8 extra bits are parity bits, so which is dropped before the actual key generation process. So actually the size of key is 64 bits, and we have to drop the 8 bits. So those bits are used for parity, and the actual length of the key is 56 bits. So this is how the parity bits will be dropped. Okay, so the pre-process before key expansion is a compression transposition step that will call parity drop. So here you can drop the bits like 8, 16, 24, 32, 64 like that, and the remaining 56 bits value is the actual cipher key, so which is used to generate the round keys. And the next operation is shift left. So after the site permutation operation performed, the key is divided into two 28-bit parts where each part shifted left 1 or 2 bits. Okay, so total we are having 16 rounds. So in 16 rounds, 1, 2, 9 and 16 shifting is 1 bit, and the other rounds shifting 2 bits. Okay. The next one is compression debugs. So the compression debugs changes the 56 bits to 48 bits, so which are used as a key for a round. Okay, so you can see the compression table here. So which can convert the 56 bits into 48 bits. Next one is DES encryption algorithm. Okay, so the left hand side of the figure, that means the plain text proceeds in 3 phases. So first, the 64-bit plain text passes through an initial permutation, so which rearranges the bit produce the permitted input, and the phase consisting of 16 rounds of same function, so which involves both permutation and substitution functions. So the output of the last round consists of 64 bits that are a function of input plain text and a key. So now the left and the right half of the output are swapped to produce the pre-output. Finally, the pre-output is passed through permutation, so which is inverse of initial permutation, and produces a 64-bit ciphertext. So the right hand side portion in which the 56-bit key is used, initially the key is passed through a permutation function. So for each 16 rounds, a subkey is produced, a combination of a left circular shift and a permutation. So this is same for each round, so but different subkeys is produced because the repeated shift of the key bits.